We're doing 8.2, Inverses of Relations. If you're one of my classes, you either got the sheet in class, you could get it off the Moodle page. If you're not one of my classes, you could copy it all down or take screenshots or something like that. Just typed it out for my students because it's a lot of writing. Inverses of relations. And usually if I draw graphs and they try to copy my graphs, it looks pretty ugly in the end. So, okay. Anywho, inverses of relations. What is an inverse? So very generally, an inverse is something that undoes or gets you back to where you started. Often you can kind of look at it as though it's like the opposite. Like if I said, what's the inverse operation for addition? A lot of people wouldn't know, but if I said, what's the opposite of adding? Well, that's subtracting. So inverse is kind of like the opposite. So the inverse operation for addition is subtraction. If you have something like, say, x is 10, if you add 5 to that, you get 15. Well, if you want to undo that, you just would subtract 5 from both sides. But usually when we're doing problems like that, it looks like that. It's x plus 5, and you undo it by going backwards. All right, I digress. So inverse operation for multiplication. How do you undo multiplication? It's division. Another one that's a little tougher often, what's the inverse operation for a third power? Well, that'd be a cube root. That's where when we had an x to the third equals something like a 125, we did the cubed root of both sides. Or you could take both sides to the 1/3 power. Alright, so how do you find the inverse of a function? And we're going to look at three different things. We're going to look at sets of ordered pairs, we're going to look at graphs, we're going to look at equations. Equations are actually more in the next section than they are here. But we'll hit them briefly today, then we get the rest tomorrow. Alright, so first part, how do you find the inverse of a function? Well, if you know ordered pairs, which make up a function, to find the inverse, you simply switch x and y. That's going to be a theme that kind of carries over into the next ones too, the points and so on. But if I have this function f, which is defined as the points 3, 7, 4, 2, 5, -3, and 6, -9, the inverse of f, or another way that you could write it, would be f to the -1, and this is read as f inverse. You could say that's the set whose members are. Instead of 3, 7, it's just 7, 3. Now if you notice, I'm not changing whether they're positive or negative, I'm just switching x and y. That's the most common mistake, is people take and change the sign on them. But 4, 2 becomes 2, 4, 5, -3 becomes -3, 5, and 6, -9 becomes -9, 6. And I end my curly brackets. So that's how you get the inverse of ordered pairs. If you have a graph of a function, to find the inverse of the graph, do the same exact thing. You switch x and y. So switch x and y. If you think back to geometry, you can save a lot of time, and I'm kind of giving it away a little bit here by having my dashed lines, which should go through there. But when you did reflections and rotations and all that good stuff in geometry, that switching x and y was what you did when you did a reflection across the line y equals x. If I look here and I have, this line y equals x, so y equals 1x, it goes through the origin with a slope of 1. You could do it either way. You could look at this and say, well, this point here should be 1, 0. So now the inverse of that is going to be, ooh, I killed that. If you look at this point, it should be 0, 1 over 0 up 1. So the inverse then is going to be 1, 0. So you could go through and just get a whole bunch of points. This point here is maybe going to be something like 2, 4. So if that's 2, 4, then my inverse is going to be 4, 2. Like that. Then over here I'd have a -2, 4, so it'd be 4, -2, and so on. So one way to do it is just to go through and switch a whole bunch of x and y's, and then try to draw either a straight line in this case or a smooth curve that should somewhat resemble this. The other way, though, that I was alluding to before is a reflection across the line y equals x, or you probably did a lowercase r, and then y equals x as the subscript back in geometry days. So if I go through and do one of those two ways, usually it turns out ugly, me trying to draw things like this with my little wireless slate. Let's see how it does here. Seen worse. Okay, so we have that one. Could go through and do that same thing here, either one. I'm maybe just going to jump out with my line. So I want to be about as far away from the line here as my other line is. And then it'll cross right at that y equals x line. So something like that. Looks pretty good. So that's what you do if you have a graph. Now, if you have an equation, this was the part that we're going to do more of our work tomorrow with. But for now, we're just going to say you switch the x and y values. So switch the x and the y in the equation. Tomorrow, we're actually going to go through kind of the four-step process for getting it in the right form when you're done. But for now, we'll simply say if you started out with something like this, f of x equals 3x squared minus 2x plus 5. Well, this f of x is really just a fancy way of saying y. So we could take and change that f of x into a y. Well, then the inverse, where this is y equals, we change the y to an x, it's going to be x equals. Instead of 3x squared, the x's become y's. So we have 3y squared minus, instead of a 2x, now it's going to be a 2y plus 5. So that would be the inverse of that function. If you had k of x equal 2x minus 3, k of x is just a fancy way of saying y equals. So it would become x equals 2y, x becomes a y, minus 3. Alright, moving on, we have Roman numeral 3. Under what conditions will the inverse of a function also be a function? So this has taken us back quite a bit earlier in the year when we looked at functions. So we're saying the graph of a function must be 1 to 1. I'm just going to do a 1-1 in interest of space, but 1 to 1. And what that means is each x must be paired up with exactly one y, and therefore it is a function. If you think back to earlier life, we talked about vertical line tests and so on, that each x value could only have one y. So each vertical line could only hit the graph in one spot, because the vertical line is going to be the set of all the values for one x value. Okay, the 1 to 1. And each y then must be paired up with exactly one x. Before we get into the graphs and the vertical line tests and so on, let's just look at these points. So now if I have this here, the set whose members are 2, 4, 5, 7, 1, negative 3, and 7, 4. Is it a function? So does each x value only paired with one y? So when x is 2, it's paired with 4. Nowhere else do I have like a 2, 7, a 2, anything else. So we're good so far. 5 is paired with 7. I don't have 5 with anything else, or an x value of 5 with any different y. So x is 1, 1, negative 3. I don't have like a 1, some different y value, and 7, 4. So is this one a function? Yes, it is. Is it 1 to 1? We do that same thing backwards. When y is 4, are there two different x values when y is 4? And yep, there is, because here I have a y of 4 with a 2. Here I have a y of 4 with a 7. So this one is not 1 to 1. It's not 1 to 1 because of those. Alright, this one, is it a function? 2, 4? No, because I have 2 paired with 4, and when x is 2, it's also paired with a negative 3. So this one is not a function. So function, no. Then it can't be 1 to 1, because 1 to 1 means it works both ways. So it's not a function by default. It can't be 1 to 1. Now this last one probably is going to be yes and yes, but let's check it out. So 2 is paired with 4. When x is 2, I don't have any different y's. 5, 7. When x is 5, there's no other y value. When x is 1, there's no number other than negative 3. When x is 7, yep, so this one is a function. And does it work the other way? When y is 4, x is 2. This is a negative 4, so we're good there, that when y is 4, it's only paired with an x of 2. When y is 7, nope. When y is negative 3, there's no x's other than 1. y is negative 4. So this one then also is going to be 1 to 1. Works in both directions. Alright, so now we're looking at the graphs. You could go through and do that same exact thing, find all the points on the graph and go back and check that, but you really want to bang your head against the wall doing that. So here, if the graph is given, apply both the vertical and horizontal line test. If you remember back to earlier, the vertical line test checks to see is something a function. And then this horizontal line test is going to be checking that 1 to 1 part. And when you have the horizontal line, it's saying, well, for this y value, are there any two different x values along that line that have the same y value? Okay, so the vertical line test to show the original as a function. The horizontal line test is applied to the original to show or to determine whether the inverse is a function. And the way that works is we talked before about flipping a graph, that if you're looking at this thing here, maybe say this, if you're doing the vertical line test on the original, this red line here, let me pull it out where you can see it. If we're doing this one here, if we take and wanted to get the inverse of the graph, we'd reflect it over the line y equals x. If I take a vertical line and reflect it over the line y equals x, it turns into a horizontal line. So doing a vertical line on the inverse is the same as doing a horizontal line on the original. Okay, that doesn't make sense, ask in class. But if we're looking at this one here, I'm going to scroll down just a tiny bit. We'll say, well, is this one a function? So if we take a vertical line, if no vertical line hits the graph more than one time, in this case it doesn't, any x value, any vertical line only has one spot on the graph. So we could then say this one here is a function, that this one is a function. Maybe I should say the original is a function. And that's because it passes the vertical line test. Now if we wanted to check out the inverse, we grab this, grabbed the wrong thing. I want to check if the inverse is going to be a function. You could go through all the work of finding the inverse, but it's a whole lot easier to just go through and grab your vertical line, or grab your horizontal line. Got derailed there. Well, does a horizontal line hit it more than once? Yeah, it's at all kinds of places. If you have this vertical horizontal line here, hits it there, and there, and there, and there. So for this y value of like 1.45, there's a whole bunch of different x values. So the inverse is not a function. And that's because it fails the horizontal line test. We could jump over to those same two tests over here on our other one. That if we take my vertical line, vertical line, it gets steeper and steeper there on the ends, but should never get to be vertical. This looks like it's an odd power function, like y equals x to the third or y equals x to the fifth or something. So then this will be the same thing as what I had written there. So the original is a function, passes the vertical line test. I'm going to cheat. Just copy that. So the original is a function, passes the vertical line test. Should have done it for real, making a real mess of the thing. But the original is a function, passes the vertical line test. Then we could take and do that same thing with my blue line. Does a horizontal line hit it more than once? It looks like it gets horizontal, but if you're looking at an odd power function, you know that it won't. So this here looks like it passes that horizontal line test. So then we could say the inverse is a function. So inverse is a function. That's because it passes the horizontal line test.